too into it. Before we get started, everyone knows A2, or you've got some kind of plan on A2, whether it's to take your extra late days or have it already turned in. It's all good. All good. Fantastic. Question. Any news before we get started? Yes.
Kaspersky?
Yeah. Tell me about Kaspersky.
Well, so it seemed something like Israel had some kind of exploit against Kaspersky where they found NSA malware in it, in the registry somehow. I'm not quite certain how that part fit in.
Okay.
But the idea is that Kaspersky has to go through the FSB and some other regulatory institutions in Russia, which are probably analogs of PRISM in the United States.
Okay.
And so, somewhere along the line, some NSA worker brought his NSA-sponsored malware development home, and supposedly Kaspersky software identified it successfully as malware and phoned home and said, hey, I found this thing. And then somewhere along the line, I'm not quite certain whether the AGB had these viral definitions or that was simply a matter of Kaspersky having it. It's a little confusing regarding who's a bad actor, who's a good actor, and what acts were actually taken by humans rather than software.
Okay, so we know that the NSA, this starts with the NSA, they have some cyber weapon malware, right? Because all of their old malware got leaked by like Edward Snowden, so we need to make some new malware. So they make some new malware, and then a contractor, actually there have been a whole bunch of leaks, maybe we should point these off here. Does anyone know where else NSA malware is leaked, or NSA cyber weapons have leaked in the last year or two? Who else is out there publishing? Good, okay, so somehow Shadow Brokers has a bunch of these. They're actually called the Shadow Brokers. These guys have a blog where they publish random pieces of NSA malware. What interesting criminal malware came out of the Shadow Brokers?
WannaCry.
WannaCry. Okay, great. So let's keep going. WannaCry came out of that from an exploit that was called Eternal Blue. Was it Eternal Blue?
Eternal Blue, Eternal Romance.
Okay, got it. So basically 2 Windows exploits in SMB, but that's a little bit beside the point here. Okay, good. So the NSA loses all their malware. They make more malware. They hand it to a contractor. The contractor takes it home to his home computer, apparently to work on his resume. They ruled out the idea that he was like trying to steal it, like he was just taking it home for stupid but innocent reasons. Takes it home to his home computer, which happens to be running Kaspersky antivirus. And then Kaspersky antivirus, and then this is a big question, somehow sees this malware, recognizes it. How does malware recognize, how does antivirus stuff recognize malware that presumably it's never seen before? Okay, what is
heuristics? Go ahead. No, they would load the thing up and then actually watch what it was doing.
Good.
I think in this case, it was preloaded with a set of code words or descriptions of NSA projects,
okay,
and was getting itself on there and then looking for evidence of those projects, and that's how they found the knucklehead who took the stuff home.
Okay, so there's the innocent explanation is that it was just doing its job. It's AV software. It looks for things that look malicious, maybe by running them in like a sandbox and seeing if they do malicious stuff when you run them, or by looking for common patterns of code or looking for things that just don't look right. When it sees such a file, Kaspersky AV is supposed to, and this is by design, send it up to Kaspersky headquarters, to their cloud whatever, which does further analysis and maybe flags it for a human being to look at. So that's the innocent explanation. The less innocent explanation is that Kaspersky actually had their AV software looking for words like top secret SCI, no form, things like that, and they actually had their software basically acting kind of as a snitch on different people's computers, and when they found the software, well, more or less the same thing happens. And then what happens to it? We think. Yes?
Kaspersky either is forced to report this to the FSB, other groups, or the FSB has insiders of Kaspersky that see this stuff and forward it along without the company's consent or knowledge.
Somehow this information leaks out to Russian hackers, is what I think was said, but they're state-sponsored hackers, and they go and they target this person's computer and they get like all this stuff. Okay, there's one more party involved in this crazy story. Who else is it? Yeah?
The people who found out that this was being done.
Who are the people who found out this was being done?
Israeli spies.
Good. So somehow, just to make this whole thing just a little bit more absurd, it turns out that Israel has hacked Kaspersky using a piece of malware, allegedly. Does anyone know what the malware is called that they used? It was used previously. It was a derivative of Stuxnet, which you guys might have heard of. It's called Dooku. And by the way, this is all based on random news stories. There's probably a lot of room for things to be inaccurate. Okay, so Israel hacks into Kaspersky headquarters, sees Kaspersky stealing stuff from the United States, and apparently sees a lot of suspicious stuff like specific, programs they claim. This is all sort of anonymously sourced, who knows. Sees Kaspersky stealing stuff from the United States, and then reports this all the way back to the United States. I don't know if it's the FBI or the NSA, and then the whole thing repeats. So like everybody is hacking everybody. It's not clear who's the winner in this. It's probably not the NSA. Maybe not Israel, because who knows if Israel lost some kind of capability. Definitely not Kaspersky. It seems like everybody is kind of worse off from this, except possibly the FSB, who seems to be doing okay. So that's the story. It's a crazy story. We don't know how much of it is exactly true or what's going on. But clearly a lot of people in DoD are banning Kaspersky. And Best Buy stopped selling Kaspersky. This has had a lot of commercial impact, and maybe it'll all blow over. We don't really know what's going to happen. So yeah, anything else I missed here? This is just like the nuttiest story. It doesn't really have any like meaningful security lesson to it. It's just nutty. Someone should make like a TV show about it. Maybe they'll use it in next year's Homeland. Okay, so yeah, any other news or related news? Yes.
There are two hackers who hacked into a Taiwanese bank and stole $60 million.
Okay.
And the way they hacked into it was literally walking into their office and planting malware on their server terminals and on their Swift terminals, so their communication
And
terminals.
Swift terminals are what kind of computer? What kind of operating system?
Isn't it server? Or
Just say Windows. Yeah,
Windows.
like Swift terminals are basically Windows boxes, probably unpatched Windows boxes that people use. So yeah, you can just get in with malware. If you get malware on the system, you own the system and your host, and so you can divert funds and whatever. Do they catch them?
They have two suspects. One of them is the chairman, one of the chairmen of the bank.
Oh, that
who
doesn't help.
suddenly has gotten about $20 million in his bank account.
Maybe he's involved in this too. Like, could be somewhere in this story. Okay, that there's a lot of things to learn from that. One of them is if you steal $20 million, don't like put it in your own bank account. Like buy Bitcoin or something. Do something that keeps it out of your way. Yeah.
In this case, would that person who installed the malware have had to have administrative rights?
It's a good question. I mean, if you have malware that requires administrative rights, then yes. But if you have a privilege escalation vulnerability that allows you to go from a user account to root, then maybe you don't. And so that's, it depends how sophisticated it was. Anything else? I'm looking for one. I'm hoping I'll get it. Yes.
Everyone who has a iPhone in this room has probably been trained to give their passwords out to anyone that asks for it.
Good. Yeah. Tell me.
Because the system iPhone, because like everyone who uses an iPhone, you are prompted for your iCloud password at completely random times in completely random apps. And you just give it, right?
Because we're basically trained to do this. All the
Yeah,
time.
you're trying to do this. Like it needs like an app that failed to download and it needs it to reinitiate the download, or your credentials expired and it needs to re-up them. But the prompt for that looks exactly the same as the alert view controller that you could make in any app.
Got it. Okay. So this means that any web page can basically, or any app can pop up a fake dialog box that basically fishes you for your credentials, sends those credentials to bad guys, and you're toast.
Yeah. And there are prompts on the system that don't even have your Apple ID.
Yeah.
They'll just say, hey, enter your password.
Yeah, I'm actually paranoid because now I'm like thinking of all the times I've entered my password and I'm like totally freaked out by this whole thing. So the answer to this is what? Like, how do you fix this kind of problem? This is a really big problem.
Make system alerts look different from app alerts, and do not allow the API that is used for system alerts to use that.
Can you really? Is that enough? Right, let's say I'm clever and I control I'm writing an app that can draw anything it wants on the screen. Why can't it draw a dialog box that looks like whatever weird dialog box Apple does? Like how does Apple make something that's not just drawings on the screen? Yes?
They do this for some iCloud stuff, which instead of saying, hey, enter your password, they say, hey, go to settings and enter your password
Yes,
there.
that's one thing. So basically it's Apple's job to train people out of using the normal stuff. But even there, right, like there's always the possibility I could trick someone into thinking they've gone to settings when they're actually still inside my app. And so this is a big problem. Like, how do you make user interfaces that are robust against, impersonation in web browsers? This happens too. People can pop up fake dialogues really easily. Yeah.
I mean, what Google does is they almost never ask you for your actual password. Most of the time, it's like if you want to download an app, it's fingerprint recognition.
Yeah.
And I mean, I guess since it's on a secure enclave, that would be way harder to.
So Apple is moving in that direction, and that helps because the Touch ID sensor has its own processor, so there's no way an application can ever control that, so that helps a lot. But unfortunately, you still have to enter your password at least once to get it initialized, so there's always the possibility that people get trained to do that. Yes?
I have a naive question. How is that even possible with the very strict policy of the App Store?
I mean, what is the strict policy of the App Store? I don't know.
So what you can do is all apps are supposedly hand reviewed, but what you can do is you can have code that checks the version number that is currently in the App Store. So that when your app is being tested, it checks against the App Store, it's an old version and it doesn't run this malicious code. But then when that app is approved by Apple and pushed to the App Store and someone downloads it onto their phone, it checks the build number against the App Store and it's like, oh, it's this new version, this code path activates. Or you could be Uber and just say, don't run this malicious code when I'm near Cupertino.
Yeah, that's another way of doing it. Yep. Or you could pull in JavaScript code. I don't know if apps can run JavaScript.
Yep.
But if it's downloaded from the internet, then you can put your stuff there. And so it will survive testing. Yeah, so I mean, more vigorous testing is probably a part of this, but yeah, there's fundamentally a hard problem here is how do you make user interfaces that share a display that can be distinguished from something somebody can draw. The only way you can tell, by the way, whether this is happening to you is if you hit the home button and the dialogue doesn't go away, then that's an indication that it's a system app, because the home button is outside of the map of what the apps can control. You can't block that. Okay, I was hoping for one more piece of news. It involves actual crypto. I was hoping you guys might have seen something about this. It just came out last night though, so I won't be totally shocked. I thought I saw something on the Piazza about this. Yeah.
Was it GPG moving from RSA to liquid curves?
No, that's cool, but it's not that. Anything else? Does involve RSA though. So you're halfway there. Anyone read anything about Infineon? TPMs? Come on, you guys. We were just about to talk about TPMs. We just started talking about TPMs. What's a TPM?
Trusted platform.
Good. And what is it? What's a trusted platform module do? We talked about it at the end of last class. You have no excuse not to remember what we talked about. Yes?
Hold keys safely.
Good.
It's like the secure enclave.
It's like a secure enclave. It's in a lot of laptops. It's particularly common in Chromebooks. And what it does is it checks, among other things, it checks that your operating system has not been tampered with when it loads it off the disk. It verifies it. It also has cryptographic keys inside of it. It can make signatures. It can do bad stuff. Not bad stuff. It can do good stuff. It can sign things like, it can tell the network, hey, this is legit, this OS has not been tampered with. And so then your network, if you connect to like a corporate network, your corporate network gets a signature from the TPM saying, oh great, now I know this laptop has a valid operating system on it, it's not being tampered with, the TPM told me that. I trust the TPM because the TPM is this, really strong tamper-resistant module that's inside of your system, and presumably it's very hard to hack. Okay, great. Well, TPMs have RSA keys assigned to them. They generate an RSA key when you start up, and that's their key. All right, how do you generate an RSA key? Remind me, step by step. How do you make an RSA key? You guys are going to need to know this very soon. And by the way, we have to talk, stop me a few minutes before the end of the class because I want to talk about the midterm and assignment 3. I'll come back to this, or I'll do it after this. How do you generate an RSA key? You guys don't remember how to generate an RSA key? Yes?
Pick 2 primes GP.
Pick 2 large primes. Not GP, P. I like P and Q. Okay, good, large primes. How do you generate 2 large primes?
Powers of 2 minus 1?
That sounds worrisome. Let's.
Okay.
Yes.
Random 100-digit number, and then run some tests on it. And
I
at
like
that
what
point,
you
it
said.
may not be primed, but it's industrial strength.
Good. So the standard way that this is done in most crypto libraries is you pick, let's say we want to generate a 1024-bit key. Well, how big do P and Q have to be in bits? You're going to multiply them together, just as a hint. How big do they have to be? 512 bits. So 2 512-bit numbers multiplied together give us a 1024-bit N. All right, how do we generate them? Well, we pick a large random 512-bit number, and we check to see if it's prime. Now, obviously, we don't pick an even number just to save ourselves trouble, but ultimately, we just pick a random number, and we run what's called a probabilistic primality test. And you guys are going to be all over this stuff. One of the tests we run is called Miller-Rabin. It's an algorithm you can run iteratively, and basically the number of times you run this algorithm tells you it does not always guarantee it outputs a prime, but the probability that it outputs a non-prime goes down as you run this algorithm more iterations. So we can get it down to like 1 over 2 to the 80 or 1 over 2 to the 128 probability, like vastly tiny numbers that this is not actually a prime. Okay, well what happens if we pick a p, we run Miller-Rabin, and it says, actually, sorry, that is not a prime. Well, we throw away that p, we generate a new one, and then we repeat the process. And based on the distribution, the number of prime numbers that in the number line, we could basically say this thing will complete in a reasonable amount of time. So this is not it's not a very inexpensive process, but it does complete on most reasonable computers. But let's say you're on a lightweight computer and you hate this idea. You have to generate a prime number. You're on a tiny little processor. You don't want to be just like doing this over and over again. Could you take a shortcut? Is there a faster way to generate primes?
You could ask someone else to generate them for you.
You could, but then that person would know your secret key. So that sounds worrisome. I want to generate it on the hardware, but my hardware sucks, and generating a prime this way will take me 2 minutes. Is there a shortcut? Well, sort of, yes. Go ahead.
Can you just like have them generating in the background?
You could,
And
but
just take them off a little list?
it still requires that you're going to have to, when you first boot up this computer, it's still going to require some time before it can start spitting out primes. So yeah, you have these possible optimizations, like you could, if you don't need them right away, you could generate them in the background. If you could have somebody else, the bigger computer do it, you're great. But you don't want to do that because you want it to be inside your TPM. Well, it turns out, let me just pull up this thing. I think there is a method for doing this, for generating primes of some questionable quality. And they look like this. So it turns out if you take a small prime, maybe I should not call this p, let's call this p prime. So p prime is a small prime. You raise it to some value r and multiply by a relatively small q. There is an algorithm that allows you to generate this whole thing. We can say p is equal to this. We can generate primes in a slightly more efficient manner if they have this particular structure. That is, p prime is a prime, r is some exponent, and q is a relatively small number. And there is an algorithm for doing this that does work a lot more quickly than this kind of just throw stuff at it and see if it's prime. And it turns out Infineon, which has a library in it, which is a FIPS certified library, does something like this. And so this, actually the full vulnerability hasn't even come out yet, but roughly speaking, this is what it does. It generates these things this way. But the problem with this, and you guys still have yet to be given this 20 years of attacks on RSA, there is an attack that works against composite moduli n, which are formed by multiplying together 2 primes that have been generated using the structure. And the reason is, what's really happening here, if you want to think about this, is you have a prime where most of the bits of the prime are known to an adversary, because you're basically taking this p prime to the r, which is, there's only so many values. P prime is usually a fixed base, and r is some reasonably sized exponent, and a relatively small q. And if you do that, the adversary has a very good idea of what the structure of this prime you're going to pick is. So there's a lot less entropy, a lot less unknown inside of it. And it turns out there's an attack, it's called coppersmith attack, that when you see a composite modulus n that has been formed using this approach, 2 primes of this approach, you can actually factor this modulus very efficiently, but only when they're done using this sort of very non-random method of selecting primes. And it costs about 40, 50 bucks to factor a 1024-bit prime, only if it's of this form on Amazon EC2. And they could actually do it for less for 2048-bit primes because of a certain detail in the way these are structured. So what this means is that all of these Infineon chips that are doing this, all these TPMs and Chromebooks, are basically screwed because there's no easy way to update them. You're going to have to throw away. A lot of these corporate laptops people are using are now toast because they no longer have secure keys. Anyone can factor them, anyone can fake signatures and do bad stuff in the name of these systems. So yeah, it's a cool vulnerability, and I'm sure there'll be more news on this soon, but just to give you a preview of the kind of things that go wrong if you don't do RSA correctly. Okay, one other thing I want to talk about. I promised I was going to talk about RSA signatures. We briefly, very briefly sketched this, and I know you guys, based on the response, the very tepid response to how do you generate an RSA key, I'm not exactly sure that very much of it sank in. So can somebody remind me, once we have an RSA key, and let's assume it's a good key, not one of these terrible Infineon keys, what do we do if we want to then sign a message? Actually, let's go the rest of the way. So we only started, we generated an actually good P and Q. What's the next step in generating an RSA key? Yes?
Multiply both of them
Good. So we
together.
compute N equals P times Q. Fantastic. What now? Yeah. En? Phi, good, I'm sorry, yes. Good, and what is phi of n? It's called the Euler-Toshin function. How do you compute it for p, if you know that this n has the structure?
PQ minus P minus Q minus 1.
Or alternatively, if you prefer, a little simpler, p minus 1 times q minus 1. You don't get easier than that. I'm sure what you just said, if you simplified it out, was that, but yes, great. Okay, good, so you've got phi of n, what now? Yes?
Find an E that's less than the totient of n and relatively prime to the
Good.
totient of n.
So let's say, don't think we want it to be 1, so let's say E in this range. Look good to you? Okay, and you said something else.
That it's co-prime to.
Good, so we want to say that the GCD of E and phi of n is 1. Fantastic. Good, so we've got our E. And now we need one more variable. What's D? How do we find D?
The inverse of E in V star Vn.
Very good. Okay, so we want to find D such that E times D, and we say is congruent to 1 mod phi of n, which is the inverse, like you just said, is equal to phi of n. How do we find this D? What algorithm, off the shelf, do we use to find inverses in these kinds of?
The extended Euclidean algorithm.
Good. Hint is yes, exactly. We use the extended Euclidean algorithm. It's actually, the Euclidean algorithm helps find GCDs. We already have to do that anyway. The extended Euclidean algorithm actually helps us find a D of this structure. Good. It's a very simple algorithm. Euclidean algorithm. Fantastic. Great. Now, just to finish up, what is the public key and what is the private key? What goes into the public key? E and N. Very good. Prefer N and E. And what is the secret key? Process of elimination, guys. What's left? D. Very good. Or if you want, you could put, the whole public key in there too, just or whatever, it doesn't matter. Good. So D. All right. Since we're reviewing RSA, how do you do encryption with RSA? You have a message M, yes?
You have a message M, and you take M, and you take its exponent. You take M, take it to the E, and then mod it N.
Okay, so we have M.
To the
Encryption is M to the public E, which is all in the public key, mod N. We'll call that C. Good, simple. This is the simplest thing I've ever seen. Yes?
Then C, to decrypt it is C to the power of D mod N.
Good, very good. So we can just use this property that M, called M prime, is equal to C raised to the E mod N. So this is invertible. This is what we call a trapdoor one-way permutation. Okay, let me break that apart a little bit. Permutation means that this process of taking M raised to the E is a permutation. If I take any value for any M in the set 1, actually I think it's 0 through n minus 1, and I raise it to the E, I will get another value, and it's 1 to 1 and on to, so it's a permutation. Has to be a permutation. Why does this encryption have to be a permutation? Yeah?
You have to be able to get
Yeah.
that information back.
You can't decrypt something if there's two different plain texts that will map to the same ciphertext. So it has to be, doesn't have to be a permutation technically. It just has to be one-to-one in some way. Okay? So, or not one-to-one, it has to be onto. So you have to be able to do this. And so tell me, what does trapdoor mean? So I said it's a one-way, I said it's a permutation. What does one-way mean? Let's start with one-way. Yes?
Isn't it C to D?
Oh God, geez, see? Last time I said that 9 was a prime, and this time I gave you the wrong RSA formula. Whatever notes you just took, fix them. That's the right way to do it. Okay, all right. Good, C to the D mod n. So we said this is that encryption is a permutation, and I said it's a one-way trapdoor, one-way permutation. Tell me what one-way means. Yes?
It's easy to compute but hard to invert.
Good. For somebody who knows only the public key, N and E, it is easy to compute this. Do you agree with me it's easy to compute this? Why is it easy to compute this? Doesn't it require me to compute M times M times M times M E times? Oh, you have another idea. Good.
Yeah, there's just an algorithm that does it a lot faster.
Okay, what is the algorithm?
To be honest, I don't remember, but I know it has something to do with like splitting it up to like powers of 2 with the exponent.
Oh, okay, okay.
Kind of like the Fourier, like fast Fourier transform, like a destination time sort of thing.
Man, you jumped right to the fast Fourier transform.
So-
But no, you're absolutely right. It is. It's a parenthesization algorithm. Okay. Let's think about it for a second. If E is small, then you could just do like the linear multiplication, right? So if E is 3, life is super simple. But in general, in classic textbook RSA, E is a random number that happens to satisfy this. So E could actually be very large. So we don't want to do like a linear number of multiplications to implement exponentiation. That would be terrible. We'd be multiplying until we died. So we don't want to do that. But let's say E is some large number, and we want to compute M to the E mod n. Can anybody tell me how we would simplify this? Let's just say, to make life easy, even though this is not a valid E, let's say we wanted to compute M to the 256 mod n, but we didn't want to take 256 steps. Yes? Sorry, what?
Shift to left.
Shift to the left, okay. Give me that in another form. Yes?
Just calculate m squared and m squared squared.
Good.
Square, square, square.
Good. So we can always rewrite 256 as 2 times 2 times 2. Okay, I'm getting tired here. 1, 2, 3, 4, 5, 6, 7, 8. Okay? I don't trust myself anymore what I'm writing on the board, so you guys just have to check me on that. So if we want, we can compute m squared mod n. And it turns out that we can take that result and we can square it again. And we can square it again. Did I write too many 2's here? Just check me on that. That's 8 of them, right? Okay. And we just square it and square it again. And it turns out we don't have to do 256 multiplications. We could do log 256 multiplications, log 256. And so we've taken something that would be linear in E, and we've made it logarithmic in E, which is actually pretty fast. It's not even the case that it's necessarily logarithmic in E. It could be even better. And what happens if this is not a power of 2? 256 is too easy. What else could it be?
The sum of.
Did I write this totally crazy? No, this is right, right? Yes. Sorry, go ahead. Yeah, sorry, losing my mind. What if it's not a power of 2?
It can be a sum of the several number, and which number is the sum of 2.
Good. In fact, what we can do is if it's not a power of 2, we can also break it up into basically a series of squarings and multiplications. It turns out that you can basically break this up into an algorithm which is called square and multiply. And actually, instead of writing it up here, I'm going to dig it out in my notes in just 2 seconds. But the basic idea is that what you do is you treat this E value as a series of bits. This happens to be something like this. And what you do, 1, 2, 3, 4, 5, 6, 7. Is that right? I'm losing my mind. But anyway, what you do is you treat this vector like a series of bits, and you work basically from one side to the other. And anytime you see a 0, that means you take the original value and you square it. Anytime you see a 1, you take your current value and you multiply it by whatever the base is, m, that you're trying to do. And I'll show you what the algorithm looks like in the slides because I don't trust myself to write it out correctly. But basically, this square and multiply algorithm reduces something from a linear number of operations down to a logarithmic number of operations for an arbitrary exponent. So it's very fast. Okay, so we were trying to figure out what a trapdoor one-way permutation is. It is computationally efficient to compute this. What does one way mean? Again, somebody said it before. Yeah.
It's hard to compute the decryption,
What is hard?
like computationally intensive.
Okay. It is computationally intensive. I take a random m and I compute this fast. If I want to go the other way, take that resulting c, and I don't know m, and I want to get back that m without knowledge of the private key, it's hard. It's computationally intensive. Be a little more computer science-y about what computationally intensive means. Yeah.
You have to solve you have to be able to factor it, which takes exponential.
So you said one good thing in there, but you're actually wrong. It does not require you to be able to factor necessarily. You can, if you could factor. I agree with you, you could compute the private key and you could solve this. It is not necessarily the case that decrypting a given C, or going from C back to E, is equivalent to factoring. This is an unknown. We don't know if RSA is equivalent to factoring. So this is just one small detail. In fact, there might be some magical algorithm that lets you go back from this to M prime without ever knowing the factorization. But what you said second was what I wanted to hear. What was that word you
It's
said?
exponential.
Good, yes. So as far as we know, the naive algorithms, at least, are not polynomial time. So we know there's a polynomial time algorithm for computing this way, but we do not know of a polynomial time to solve RSA for a ciphertext. It's the encryption of a random message. We just don't know of a polynomial time algorithm. One small detail, it's not necessarily exponential time, but in the super polynomial, there's actually a funny class of super polynomial time algorithms that sits between exponential and polynomial. And the best algorithms we have for inverting RSA fall into that weird category. But they're still not polynomial time. And so as a result of this, if you choose your n large enough, and you pick your p's and q's properly and not using stupid things like Infineon did, we have an algorithm that is one way. You can go this way easy, and going this way without knowing the secret key is hard. So I told you this is a trapdoor one-way permutation. I hope someone is writing that down. We've gotten one way. We've gotten permutation. What is trapdoor? Yeah.
It becomes easy if you have some other piece of information.
Good. So like we talked about, this notion of a trapdoor in cryptography means that there is a magic secret. So it's hard for everybody else who doesn't know this secret, but it's easy for you if you know the trapdoor. If you can sneak in using your special magical trapdoor, you can undo RSA in polynomial time. And the way we do it is we basically just compute C to the D because we know D. If we didn't know D, we'd be stuck. Okay, so that's what RSA is. So we've talked about RSA encryption. We've talked about RSA key generation. We kind of, for like 2 seconds, talked about RSA signature. And I want to just go over that quickly. So we've got encryption, but I don't care about encrypting things. I want to sign things. What does signing mean? What kind of primitive is it? Yes?
It means that it's an authentication for me. I sent this message which uses my public key actually came from me and not someone else.
Good. So if I know your public key, you've given it to me in a trustworthy way, and you send me a message with a signature on it, I can be assured that only you could have possibly made this message, right? Because I'm guaranteed that only the person who knows the secret key, unless you lost your secret key, but otherwise you are the person who made this. Okay, with Max, what's the difference, right? So with Max, what is the difference there? Do I know, if you send me something that is mapped, do I know you made it?
No.
Okay.
You know.
Let's make this concrete. You give me a signed confession, right? Saying that you broke into, I don't know, the bike store, okay? I have your signed confession, digitally signed with an RSA signature. Can I take this to a court of law and convince a judge that unless you gave out your secret key, it really came from you?
Yes.
Seems good. What if I have a MAC'd confession that is produced by you?
You could say that the accusation is definitely that I robbed a bike store, but you can't say that I confessed.
Why not?
Because the MAC is just saying that the message was not changed. It verifies the integrity of the message, not the authenticity.
A little more concretely, what's the difference? Yeah.
I think you need the secret key for the signed person.
Good. So in order for me to verify your confession, that it was actually MAC'd or signed, in order for the judge to verify it, they need to have, in the MAC case, they need to have the secret key. So at least, in the case of a Mac, at least one other person shares your secret key. So that means I could have made the confession and Mac'd it, or you could have made the confession, or if I give the key to the judge could have made the confession. Anybody who can verify the thing could also have made a forgery of it. So there's no guarantee you made it. With a digital signature, anybody can verify it using only the public key, but only the person who has the secret key could have actually made the signature. So that means I could not have forged it, the judge could not have forged it. Does anyone know what this property is called?
Non-repudiation.
Good. It is called non-repudiability. Repudiability. Oh my God, I can't write this much. Okay, non-repudiability means only the person with a secret key could have made one of these signatures. Macs don't have this property, but signatures do. Do we always want non-repudiability in our protocols? Is it always a good thing? If I text you and I say, hey, I'm about to rob a bike store, do I want necessarily that to be non-repudiable? No, I don't. So actually a lot of protocols like WhatsApp and Signal actually make a point of not using signatures. They use Macs. Specifically, not so much because people are going to rob bike stores, but specifically because they don't want to be responsible for somebody coming along and saying, hey, I have cryptographic proof that Matt did this thing. It's like all the scandals we read about where like texts are posted, those scandals at least don't have digital signatures attached to them, and largely because the cryptographic protocols we use make a really, really strong point of avoiding adding non-repudiability to them. But anyway, that's detail. Good. So RSA signatures. We know what RSA signatures are. How do we make an RSA signature on a message M? What does the signing algorithm look like? Yeah.
We take M and we hash it.
Okay, good. I like it. We don't always have to. Let's go to the textbook one. Let's not worry about. What if we're just doing textbook RSA before we get to hashing? Yeah.
You like encrypt it with your secret key?
Good. So the textbook version of RSA, what you will literally read in your textbook, is you just take M to the D, which is what I accidentally wrote before, mod N. Okay, the idea is only I have D, and so only I could perform that operation on a given M. So clearly this is non-repudiable or ish, looks non-repudiable-ish. And then the verification algorithm is what? Call this sigma, signature. What do I do?
Go backwards.
Go backwards, and I go backwards by taking sigma, raising that to the E, mod N, and checking what?
It's the same as the message.
It's the congruent to the message that you gave me, mod N. Fantastic. So verification is super simple. That's great. Now somebody mentioned, we talked last time very briefly about attacks on this, right? These signatures are not great signatures in one sense, which is that it's possible if I sign a message M, can you do something to my signature that would maybe cause it to be wrong or do something? Is there anything you can do to these signatures? Actually, I don't know. Is there? What can you do with these signatures that's bad? What do you not want people to be able to do with signatures?
Change them.
Change them. Good. So we've talked about this idea of malleability, of being able to take a message that's been encrypted or maybe signed and fool with it to make a different message. Can you see an attack on classical RSA that lets me do that? What could I do? Yeah.
If you're allowed to flip a bit, you could just flip a bit in the signature.
I don't see how that's going to work. If I flip a bit in the signature, it's probably not going to verify with the message.
Right.
Because it's a permutation. Changing any part of the signature will result in a different thing when I compute that to the E. So that will not naively work.
Oh, message malleability, not signature malleability.
Well, I mean, both, right? I want to make, you've given me messages and signatures, and I want to make a new message that you never signed. That's what I want. I don't care how different it is. It just has to be a valid message and signature that you did not make. Let me give you a little hint. So let's say I get you to sign, let's say we're going to sign integers because integers are easy, right? So let's say I get you to sign M1 equals 10, okay? And I also get you to sign M2 equals 20. And maybe I'm claiming that this is a bet. You're making a bet with me, right? So we're betting. I got you to bet $10 in the first bet. I got you to bet $20 in the second bet. Okay, but now I want to make a provably valid message and signature that claims you bet a lot more than that. Is there anything you could do? What does the signature look like on M equals 10?
Can you add them together?
Just multiply it.
Very good. So M, this would be, the signature would be equal to 10 to the D mod N. And this other signature, called a sigma 2, would be equal to 20 to the d mod n. And you just said, what happens if we multiply these two signatures together? And also, we make a new message. I'm going to call this M3. This is our forgery message. Okay, M3 is equal to the product of these two messages, and the signature is equal to the product. Sigma 3 is equal to the product of these two messages. Does this new message and signature pair verify? If I compute that signature to the E, does it work? Does it work out with respect to message 3? Does it verify correctly? Yes? No? Yes, it does. So I've made a new signature out of two previous signatures. I made a new message as well. And so I can actually take pre-existing signed messages and make new ones. In the case where I bet you $10, then I bet you $20, now you have a signed message that claims I bet you $200. I never bet you $200. But if somebody takes it to a judge with a signature, this judge is going to now believe, because it's a non-reputable signature, that I did bet you $200 and not $200. Yeah?
So I have two questions on this. So one is, that's assuming that the entire message is comprised of that value and that it's encoded in binary, right?
Sure.
And the other question is, if your signature is your message to power D, is that the entire message? Is that like the product of just like the last block?
We're using toy examples here. So this is really, when I say textbook RSA, these are it's kind of a toy algorithm. You wouldn't actually use textbook RSA for this reason. And similarly, I'm using kind of toy examples where I'm signing numbers, right? That's great in a cryptography textbook. In real life, your message is probably going to be a lot more complicated than a number. And so multiplying two like meaningful messages together is probably not going to produce something very useful, but maybe it does. Maybe you're clever and you found a way for it too. The point here is that we can't make a general claim that this signature scheme is unforgeable, because there is this property. It's a very specific property, but there's this property that you can multiply together messages and signatures and get new ones. Whether they're useful or meaningful, I don't know, but we can definitely get something, and that's not good. So how do we fix this? Somebody mentioned hash functions. Okay, so what we can do is, instead of using just raw messages like 10 or 20, we can do other stuff. And there's a bunch of different ways of doing this. But the very common way is, first of all, we don't sign M. We compute hash of M. And oftentimes, we're also going to concatenate onto this some padding. This is the classical kind of way that most RSA signatures in real life are actually done. You take a hash and you concatenate padding, or you may do it the other way around. There are specific reasons for why you might do that. And you take this whole thing, turn it into an integer, and you raise that to the d mod n. And then you give somebody, m, and they verify by recomputing the hash of m and concatenating the padding, which hopefully is a fixed value and not random. And then they check to see when they raise this to the e that it matches. And what this does is it makes it very hard. These malleability attacks over here, they still exist. It's still possible to make new messages. But the hope is, if the hash function is good and the padding is good, it should be very hard for somebody to manufacture, by multiplying two existing messages together, it should be very hard for them to manufacture a meaningful new message that actually checks out as having the right padding and goes through the hash function correctly and so on. It just makes it much more difficult.
So I wonder if you multiple two text messages together, what will you get?
Two text messages?
Yeah.
You get a bunch of junk. I mean, generally speaking, these attacks are not by themselves useful, but there are practical attacks where people take binary data structures and they multiply them together and they mess with them and they get like a new binary data structure. Because oftentimes, like, a binary data structure is like a length byte followed by some data followed by like another length byte. And so when you can do multiplication of things, you can often make a new ciphertext that just happens to have the right length byte on it, and like you can sometimes get lucky with that kind of attack. So these things are not totally outside the realm of possible. So typically using a hash function and some padding is the fix. It's not a provably secure fix, but it's a fix that most people use, and it mostly solves the problem. I want to show you one other thing that tends to go wrong with RSA signatures. If you are verifying, I want to show you, let me see if I can get the actual slides up here. If you are verifying an RSA signature, and you have done this hashing thing and this padding thing, oh god, hang on a second, let me bring this up. One sec. So I want to show you what these actual RSA padding schemes look like because it's helpful and you'll actually see this and you're going to need to know it anyway because I'm a sadist and I'm making you guys do this stuff. Please work. What's that?
It's warm enough.
Yeah, it takes a little while. There we go. Okay. Oh. Okay, good. So this is the RSA algorithm. Just a reminder, phi of n equals p minus 1 q, whatever. We've got p minus 1 times q minus 1. We've got our public key and our secret key, and that's what signing looks like. Traditionally, s equals m to the d mod n. We use RSA for all kinds of stuff. Okay. Now, I'm going to show you, this is a padding scheme that is actually used. This is the concrete padding scheme that is used in RSA signatures, in TLS, in almost every application where we actually run into this. And it's stupid. Okay, it starts with a 0. It goes to a 1. It has a fixed sequence of bits, which are all in hex, FF, 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 and so on. And it ends with a 0. And then finally, at the end of this, we have a hash of a message, which if we're using SHA-256, would be a 32-byte hash of the message. Why do we have this padding, by the way? What are we doing with all this padding? What's the point of it? No, it's not for block cipher. We're going to take this. What we have is, really we have a hash of the message. This is the payload of what we're signing. We've hashed this thing using SHA-256. Why don't we just take the output of SHA-256 and feed that into the RSA signature algorithm? 32-byte hash to the D mod n. Why don't we do that?
Because they could calculate the hash of the message from the message itself, and if they're generating that, that might give them some.
The answer is there's some very specific attacks when the messages, when RSA messages are too small, when they're too short. A 32-byte message going into a 1024-bit RSA modulus could, in some cases, be too short and could enable some attacks. And so we kind of mentioned this happens in the encryption case. We don't want that to happen, so we want to make sure that the integer, because remember, ultimately RSA works with integers. We want to make sure that this integer m that we're signing, this thing, is large. And that's really all the padding does. It starts with a 0 byte, which I think is stupid, but it starts with a 0 byte, and then immediately after that there's a 0, 1. When you think about this as an integer, that ensures that this is going to be a large integer. It's not going to be a small integer. Even though this is only 32 bytes long, the entire thing is going to be close to 1024 bits in length. So we're adding padding just to basically fill it up to that space. All of these are fixed, and then we end with a 0 to tell us, okay, now the hash is going to come. So if you're reading this, you're going to do what? How are you going to parse this? You're writing a parser to actually verify. So you've taken this thing, this padded message, it's been raised to the D, and you've gotten that signature. You're going to raise it to the E to verify it, and you're going to check the padding is correct and the hash is correct. How do you write that checking code? Yes?
You just like jump straight to the location that the hash starts?
Okay. So you're going to go all the way to the right, and you're just going to check these 32 bytes, and you're going to ignore the rest of it.
Oh, good point.
Yeah, you don't want to do that because there's yet another class of attacks that if the adversary can monkey with this padding and send you like arbitrary padding, and you don't check the padding, they can actually do a whole bunch of attacks. Coppersmith has an attack where if they can change this padding arbitrarily without you noticing, then they can actually forge messages. So you must check that the padding is correctly structured. How do you write this code to check that the padding is correctly structured?
Memcomp.
Memcomp what?
0x, so your values, all the values up to the hash are fixed, so it's just, hey, does this literally fit exactly the same?
I don't like you, because that's what I was hoping nobody would say. So what are you going to do besides memcomp? What are you going to do if you're the ordinary programmer? You're not going to want a memcomp.
A string compare, which would truncate after.
Oh, yeah, don't do that. Why would string compare not work here?
Because you've got embedded nulls.
Yes. So what actually happens when you do stircomp? If you do stircomp, if I make a check buffer that has all the padding that I'm supposed to see and the hash I want to see, and I do a stircomp of these two things, what happens?
It's comparing out to the end of the string, which.
To the end of the string?
Or to the first null.
And where's the first null?
It's your first byte.
So is it actually going to do anything? No. Okay. So we have two proposals here. We have fill a buffer with all of the expected padding and the hash of the message we've been given, and do a memcomp.
Can't you skip the first byte?
What's that?
Can't you just skip the first byte?
You could skip the first byte, and that would work fine up until here. But then you'd still not be comparing. Okay, so we have proposal one, which is this memcomp thing. We're going to put that aside for a second. I like that. Your proposal, which I know was just a counter proposal, which was
Yeah.
do the same thing, fill a buffer, and use strcomp. Sounds kind of worrisome.
I
Let's not do
mean,
that.
you said what would a lazy programmer do? That's
Well,
the
what does
only
a lazy
reason why.
programmer do? You guys, no, come on, think about a lazy programmer. You guys are throwing things in buffers and comparing them.
Use a library?
Well, and what is that library going to do? So the typical programmer does the following, and this is done over and over. They say for I equals 0 to n, check that I0, or this one is 0, check that this one is 1, check that all of these are f, and when I see the first 0, wham, I know that I've hit the hash, and the next 32 bytes are going to be the hash. Okay, why is that a problem? Yeah.
Put a 0 somewhere in the fixed padding and create your own hash.
Good. If you're a bad guy, again, there are sophisticated attacks you can get by like multiplying stuff together, where you can cause this hash, or what looks like the hash, or what this is really this 0, to be way over here. And if you can force this to be way over here, and you happen to be using a small modulus like e equals 3, there are these attacks where you can actually put a forger, someone who doesn't have the secret key, can forge a signature by putting what looks like a hash all the way over here, and thus they can actually forge arbitrary signatures. So if you're going to use a small modulus, you have to make sure that this thing is right justified. You have to make sure that all the padding is correct to avoid these attacks. You have to make sure every bit of this expected thing is the way it's supposed to be. You guys kind of jumped me a little here because these are the things you have to do. Okay, so I mentioned this vulnerability. This is actually due to Bleikenbacher. Bleikenbacher's vulnerability is when e equals 3, and you don't check that the thing is right justified, you can actually forge signatures where the hash appears in the middle of the message. That's what I just mentioned. Okay, so the question is how to fix this. You guys kind of jumped me because you said, well, in general, what you do is you would want to make sure, since this padding is fixed, you fill up a buffer with all the bits of the expected padding and hash you'd expect to see, and you would do a strcomp, right? I can't believe you guys totally ruined my surprise on this. Okay, you don't do a strcomp because, of course, strcomp goes badly, right? You don't want to do a strcomp, but it turns out that lots of people do this. Let me see if I have an example of one. Hang on a second. We had a system for doing software padding, and the developers at We did exactly this. They had an RSA signature where they did the padding in this way. They put it into a buffer, and they called strcomp on the 2. And the end result was that it basically only checked, it basically ends at the first 0 byte in the padding, which is here, and they actually, in fact, they only checked this portion of the message, which meant they were vulnerable to changes in the padding. And their strcomp ended when the first 0 appeared in the hash. Okay, how do you exploit that vulnerability? Where you're only checking the hash of the message, ignoring the padding, and you're using strcomp. You're trying to attack the Wii. You're trying to get Linux running on the Wii. And you're using the software update infrastructure that Nintendo has created, and you want to make a signed message for your arbitrary software that verifies with Nintendo's key.
You could steal a signature from a verified one that had a null byte as the first bit of the hash, if you get lucky, or one null byte that is close to the beginning of the hash and just force a collision because you have a small hash.
And that is exactly what they did. They found a signature where the hash, the message that was being hashed in that valid signature, had a null byte. Maybe it wasn't the first byte, but it was like the second or the third byte. And then they took their software, and they made sure that their software hash also had a null byte, like was the same set of bytes up through that null byte position. It differed after that position, but it was the same. How do you make your software have a hash of that structure? I'm writing my malicious software. I want to get it to run on the Wii, and I want the hash of my software. Let's say the structure of your legitimately signed message was something like 23AE00, and then some other bytes. So there's a 0 in the third byte of the hash of the actual signed legitimate message. And you have written some software, let's call it S, and you want the hash of S to match 23AE, and then really it doesn't matter at this point, but yeah, 0, 0. So how do you write software where the hash of this software is guaranteed to have these 3 bytes in the first bytes of its SHA-256 hash? How do you construct software with that 3 byte prefix hash?
hash, like add on some garbage and check it. And see-
Good. There's lots
Yeah.
of junk in software that doesn't really affect the software, right? There's strings, there's random fields, you can always add on some stuff. Basically, you just brute force it. You try hashing S, you see if it works. If it doesn't, I don't know, maybe we'll just concatenate on like a counter to S. And then we'll increment this counter, and we'll see if it hashes right. We'll increment it again. We'll just keep doing that. If we have to match 3 bytes, in expectation, how many times are we going to have to guess? How many times are we going to have to hash before we get one that works? If we assume the hash function is really high quality, random looking function.
Wouldn't this change S though?
Yeah, but it's okay, right? Like if this counter is at the end of S, and let's say it's in a place in S where it doesn't affect the operation of the program, which there are lots of places you can always tack in some junk that's not going to break the program, right? Then we can just change it arbitrarily, it won't matter.
Wouldn't you just need to try 256 to the third, or?
Yeah, basically. Which, come on, 256 to the third, we don't do things base 256. So yeah, so 2 to the 24.
24th, right?
Yeah, on
Okay,
an
got it.
expectation, we'd have to try 2 to the 24 possible pieces of software. How long does that take? Not very long. They did it in like 10 minutes on a PC. And they were able to make software that, because of the vulnerability in this verification algorithm, was actually considered as valid signed code by we. This kind of thing happens all the time because people basically screw up in how they implement RSA. There are lots and lots of attacks on RSA. It turns out that this PKCS number 1v1.5 padding for signature stuff is really vulnerable to these attacks when E equals 3, and you don't do everything correctly. But if you do everything correctly, there are no attacks. Yes?
How does it be learned those 3 bytes again?
Oh, remember, when Nintendo hands out a legitimate piece of software, they give you the software, right? And they give you the signature. You have that stuff. So you can always compute, if you have the legitimate software, you can always hash that, or you can always check the hash of that, and you'll be able to see, okay, the hash of that is these 3 bytes, and that's how you learn the 23, this stuff. And then you just have to make your own malicious software have the same first 3 bytes as that software. That's the attack we're talking about. Okay, so this stuff happens all the time. Okay, so this is basically what we have to do with RSA in order to make signatures. What if we want to make a signature and encrypt all at the same time using RSA? What do we do? Do we ever want to do this? Do we ever want to sign and encrypt stuff? Yeah.
Would that like cancel out?
If we used our own key, yes, it would cancel out. Okay, generally speaking, it is not considered good practice to use your own RSA key for both signing and for encryption. Like, you can generate an RSA key, you should pick one. You should not do both. However, lots of protocols do. TLS, for example, does actually allow this to happen. You can make a TLS certificate, and if you use Diffie-Hellman, the Diffie-Hellman modes of TLS will use signatures based on your RSA key. And if you use the RSA modes of TLS, it will use encryption based on your RSA key. So there are a lot of people who kind of violate these principles of using both these things for different purposes, or not using the same thing for different purposes. Let me just see if there's anything else. Yeah, it doesn't matter too much. Okay, good. So I think we kind of covered everything that I want to cover about RSA. Do we have any RSA questions? Because I'm setting you guys up to actually do some RSA implementation. And I want you guys to not feel like I'm under-preparing you. Yes?
How do you multiply 512-bit numbers when you don't have a 512-bit type?
Oh, you get a 512-bit type.
Okay.
I mean, how, right? So how many programming languages don't have a 512-bit type? Does Python?
So there's a GNU arbitrary precision library for C, and I assume if we're this far into the class, there's one for Golang.
Oh, crap. Yes, there is one for Golang. It's kind of horrible, by the way, and you guys should know that if you use the arbitrary precision, it's called Big Num library for Go.
Yeah.
You have to pass these things by reference, pass as pointers. I learned the hard way this summer, and I tweeted about it a lot, where I was like, I hate Go. Go's the worst language, because I was passing things by not reference, and they were like getting trashed. Because these structures, basically, the answer to your question is, you use either a language that has built-in like arbitrary precision types, or you use a library that has big nums, and big nums are basically just data structures where you can store arbitrary length integers. They have basically a length in bits and then a blob of data that represents the integer. And they include fast algorithms for multiplication and so on. So I am going to ask you in the next assignment, which is going to come out soon but be due after the midterm, to implement RSA. And implementing RSA, based on what I've said, should be pretty simple. However, I'm going to make your lives a little bit more difficult in two different ways. First, I'm going to ask you to implement square and multiply yourself, so don't use the existing exponentiation routines. It's not terribly hard, but it'll help you a lot when we move on to side channel attacks, which we'll move on to soon. And then the second thing is I'm going to ask you guys to implement the primality testing, finding prime numbers. So in short, you're allowed to use a big num library, but the only thing you're going to be allowed to use it for is the generation of random numbers and multiplication. Everything else you're going to have to do yourself. Okay? And you're also going to have to implement like some other stuff using a different algorithm that's not RSA, and you'll see what that looks like. It's not terribly hard. Okay, cool. I want to talk for a few minutes about the midterm. The midterm is coming up next week. Somehow that happened really fast. Sorry about that. It's on the 18th. We've covered a certain amount of material at the time. I'm going to put out kind of a list of things that are explicitly what we need to have covered. But I think if you've been coming to class, you should have a pretty good idea of the material we've covered so far. Let's see if we can make a list. By the way, somebody asked me about slides, and all of the slides that exist thus far are up on the GitHub page as of like a couple days ago. So you have the slides. Sadly, we did a lot of stuff on the board too, and none of that stuff exists except inside of your wonderful notes, which I'm sure you've been diligently taking. So hopefully you guys can figure that out.
I'm going to try and get the rest of the videos updated. I've got one video that for some reason I bumped it and it's cut into two. I'm trying to figure out a way to splice that back together, but the rest of them should be up as of today.
Okay, you're welcome to rewatch all the videos. That sounds horrible. I don't know why you're going to do that. I think notes would be easier, but what you guys want to do. Okay, let's quickly talk about things that we have covered in this class. So we have covered the basics of, underlying things like one-time pads. You should really understand a one-time pad, why it's secure. You should understand symmetric crypto. There's two M's in symmetric crypto. You should know that. Symmetric crypto, okay? So what algorithms have we talked about? People, quickly. Talked at least three underlying crypto algorithms. Remember them? AS and DES and
Visionaire?
Visionaire. Well, let's not use Visionaire for anything serious. And
Triple test?
I think we might have mentioned RC4. Did I mention RC4 once for 2 seconds? Well, if I didn't, I'll mention RC4. Okay, so things like that. Or as an example of a stream cipher, AES counter is another one of these. Okay, so what other things did we talk about when we talked about block ciphers? We spent a lot of time on them. Yes.
CBC mode.
CBC mode. We talked about counter mode. If I give you any arbitrary mode that you have not specifically done in this class, and I say, hey, look at this mode, hopefully you guys will be able to reason about different modes of operation as long as they're pretty straightforward, because there are other modes that we haven't talked about. Okay, symmetric crypto, modes of operation. Fantastic. What else? We've talked about MACs. You should have some idea what the properties of a MAC are and how these things work, at least at a high level at this point. What else did we talk about? Oh, yeah, we talked about how to combine things together.
Encrypt and MAC, MAC and encrypt.
Very good, yes. And if you think I won't ask you a question about that, you guys are tripping, so please remember that's something I care about a lot. Combining these things. What else? What else? We talked about hash functions. I hope you guys remember your basics of hash functions. We talked a lot, or a little bit, about asymmetric crypto or public key crypto. What algorithms have we talked about?
RSA.
Really? Yes, we have talked quite a bit about RSA, signature and encryption and key generation. You guys should be experts in this. What else?
Diffie-Hellman.
Good, and that's it pretty much, right? We haven't, spent a lot of time so far talking about this. And what else? We've talked a little bit about hardware, and probably over the next, I guess we have one more class before the midterm. We're going to be talking a bit about software and maybe some about side channels. So everything is kind of fair game up through the Wednesday class, and there's a bunch of reading which I've not been really yelling at you about, but I want you guys to look at and be aware of because a lot of that stuff is important. There is also a reading which I keep promising to put up, and I'm going to give it to you today so you have it by next week, which is the RSA attacks paper. You could just basically Google it at this point since it seems like I'm incapable of remembering to do it. It is called 20 Years of Attacks or something like this on RSA. It's by a guy named Dan Bonet. And it summarizes a lot of cool stuff, and I'd like you to know a lot about RSA. That's pretty much it. There may be some random stuff that we've discussed, like password hashes. I know we spend a lot of time at the beginning of class talking about random things, like how to do password hashes securely and like hardware and random things. Those actually matter. So, you know, be aware, like when we discuss something in class, it's kind of fair game, as well as talking about. Anything else? Any questions about that? Okay. Good. So next time we're going to either be talking about software and side channel attacks, and I'll let you guys go a few minutes early.